Bismillahirrahmanirrahim. Assalamu alaikum dear students. This is your instructor Anisa Nawaz from Department of Physics. This is our lecture number 10 as our first chapter has been completed. So this is our first lecture related to chapter number 2, vectors and equilibrium. After completion of this lecture, you would be able to explain difference between scalars and vectors, describe the Cartesian coordinate system, and you would be able to explain some basic types of vectors. Okay, so first we should know that what are physical quantities, as we have already done in detail in chapter number 1, that physical quantities are those quantities that can be measured or quantified. All those quantities that can be measured are known as physical quantities. And if we are going to categorize these physical quantities, that can be categorized as scalars and vectors. Okay, so physical quantities can be divided into scalars and vectors. So what are scalars? Scalars are quantities which have magnitude without direction. Those quantities which have magnitude without direction, only magnitude is enough for their complete specification. For example, temperature, mass, kinetic energy, time, amount of substance, density, charge, all these are scalar quantities. If we are going to describe a scalar quantity, only magnitude is enough. For example, if we are going to a shop and over there we ask for 5 kilogram of sugar, 5 kilogram, its magnitude is just enough for complete specification. So no need of direction. So we say that scalar quantity in physics that has magnitude only. It means that number value with units. For example, if we are having speed, its magnitude is 35 meter per second. We are talking about speed over here, not velocity. Velocity is a vector quantity. Distance 25 meters and age 16 years. All these are scalar quantities. What about a vector? A vector is a quantity that has both magnitude and direction. Such quantities which need magnitude as well as direction for their complete specification. Without that, we cannot explain it completely. Okay, for example, velocity, displacement, acceleration, force, torque, momentum, all these quantities, all these physical quantities require direction for their complete specification. Without that, their explanation is incomplete. So if you are talking about force, which is a vector quantity, so all types of forces, whether it is acceleration, deceleration by force, gravitational force, frictional force, torque or rotational force, all these are types of vectors, examples of vector. Okay, so all those physical quantities which need magnitude as well as direction for their specification are known as vector quantities. And if we are going to compare scalars and vectors, how we can do that? Let's say that we are standing at the center of this area, we are standing here and we have to go to the library. We want to go to library and we know that a library is 0.5 miles away from this point. Okay, we are having its magnitude, we are having a scalar quantity. Distance, we know the distance, which is 0.5 miles, but we don't know the direction, we don't know where to go, we don't know that in which direction we have to move 0.5 miles. Over here, vectors are required. Without vectors, we cannot explain it properly. Okay, so for complete specification of a direction, we need a vector. So how to get to the library? Need to know how far and which way. How far is a scalar quantity, distance, and which way? It is basically the direction, a vector quantity. Okay, so what are scalar? Number with units, and vector, quantity with magnitude and direction. So what was there? We need a vector for some quantities. Without direction, without vectors, we cannot explain certain quantities. Okay, So that we can say that vectors are playing a very important role in mathematics as well as physics. Both subjects need vectors for their complete specification of some physical quantities. Okay, so if we are going to differentiate between scalars and vectors, how we are going to do that? Let's check it out. Scalar and vector quantities. Quantities that can be measured are known as physical quantities, which can be categorized as physical quantities are categorized as scalars and vectors. Okay. For example, if a car is moving and it is covering some distance, that distance is a scalar quantity. Okay, but if we are checking out its direction, in which direction it is moving, we are checking out its velocity and its displacement. Both require direction, so these are vector quantities. And if we are going to differentiate between scalar and vector quantities, scalar quantity has only magnitude, vector quantity has magnitude as well as direction. Scalar quantity change by change in their magnitude. Okay, if magnitude is changed, scalar quantities are changed, and vector quantities are changed by change of either magnitude or direction or both. So if we are going to change its magnitude or we are going to change its direction, then vector quantity will be changed. Okay, and what about scalar quantities? They are added or subtracted by laws of ordinary algebra. We can simply add or subtract by using simple mathematics, plus, minus symbols and all these things. We can use ordinary algebra to add or subtract the scalar quantities. But what about vector quantities? They are added or subtracted by laws of vector algebra. They cannot be added by simple algebraic operation which we are using. Okay, we have to use different techniques which we will discuss later in this chapter. Okay, so if we are going to represent the vectors, they can be represented by two ways, symbolically or graphically. How we are going to represent the vectors? Symbolically or graphically. Two ways to represent a vector. If we talk about symbolic representation of vectors first, then let's say that vectors are typically written in equations or labeled on diagrams by a letter with an arrow on top or on the bottom. Okay, so you can say that we are going to represent vector either by arrow on the top or arrow on the bottom. Both are the ways to represent, but in your book we are just going to represent the vectors by arrow on the top. This representation will be used in your book. Okay, and second way can be represented by bold-faced letter. We can represent the vector by a bold-faced letter. Okay, so we can represent the vector by a bold-faced letter, so which you are not normally using because it is difficult to make a bold-faced letter on your notebooks. So we are usually using the representation like this. Okay, a letter with an arrowhead on the top. Okay, if we are going to represent, we are talking about symbolic representation. If we are going to represent magnitude and direction of a vector, how we are going to represent that? Direction of a vector specified with alphabet with cap head. So we can specify the direction of the vector by using a hat. You can see over here, this can be read as a hat, a cap, whatever you want to read it, a hat or a cap. This is representing the direction of the vector. Magnitude can be represented by the vector symbol bracketed by two vertical lines. So this symbol is basically representing the magnitude of the vector. Okay, so vectors express symbolically. This is the magnitude. Okay, two brackets with vector, so we can say that vectors can be expressed symbolically as vector is equal to, we know that for complete specification of a vector we need its direction and its magnitude. Okay, so this vector can be represented as magnitude multiplied by direction. So this bracketed symbol, it is representing the magnitude of the vector, and this a hat or a cap is representing direction of the vector. So this vector A is completely specified by its magnitude as well as its direction. If you are only writing the magnitude, it will become a scalar, and we cannot completely specify it without its direction. Okay, so for complete specification we need direction as well as magnitude. And if we come to graphical representation, in graphical representation a vector is represented by an arrow. The length of the arrow is the magnitude, and the arrow itself indicates the direction. Okay, we can represent arrow by graphical representation by drawing an arrow. Okay, and the length of the arrow is its magnitude, and arrow itself indicates the direction. For example, if we are showing the force, so this vector, which is this arrow, this is basically representing the direction of weight. Weight is a vector quantity. Length of this vector is showing its magnitude. Okay, 45 Newton, and it is acting in the downward direction. So this arrowhead is representing its direction. So length of the arrow is telling us about the magnitude, and arrow is telling us about the direction. And we are having another force over here. This force is representing the you can say length of this arrow is representing the magnitude, and arrow itself is representing the direction. Okay, so we can say that vector can be represented graphically by using an arrow, length of the arrow, magnitude, direction of the arrow, direction of the quantity which we are using. Okay, and the starting point of this arrow is known as tail, and the ending point of this arrow is known as head. This is the tail of the vector, and this is the head of the vector. Okay, so tail and head of the vector. So we can say that vectors are represented by drawing arrows in the direction of the physical quantity. Starting point is tail, ending point is head. Okay, starting point is tail and ending point is head of this vector. So vector quantities, how we are going to identify that? Identified by bold type with an arrow above the symbol. For example, this velocity is showing is shown over here, v with an arrowhead on the top. This is equal to 23 meter per second, magnitude northeast. Okay, the direction is northeast. So velocity with magnitude as well as direction, this is the complete specification of a vector. So the vectors which are considered without reference to coordinate axis, we are not referring it. There is no specific starting point, no specific ending point. Such type of vectors are known as geometric vectors, just drawn like that without any coordinate axis. Okay, so what is axis? Any set of values that indicate the position of a point in any given reference system. So the set of values that are indicating about the position of a point, like you say xy plane and all these x-axis, y-axis. So these are set of values that indicate the position of a point in any given reference system. We will check this out. And second type of vectors is algebraic vectors. The ability to use vectors in applications usually required us to place them on a coordinate plane. These are referred to as algebraic vectors. We are going to put the vectors on a coordinate plane. We are specifying its starting point, we are specifying its ending point, the location of the point. For that we need a coordinate plane. So such type of vectors are known as algebraic vectors. Okay, those which do not need the specification are geometric vectors, and those which need the coordinate system, that they are basically known as algebraic vectors. Okay, so coordinates were used by mathematicians to analyze physical situation in about 14th century. So first these coordinate systems were used in 14th century, and afterwards they were widely used in the field of mathematics as well as in the field of physics. Okay, So development of methods used with coordinate systems is credited to French mathematician René Descartes. Okay, so a lot of work was done by him. Cartesian coordinate system, the coordinate system which we are widely using. You are aware of this type of Cartesian coordinate system. Okay, it is also called the number plane. Cartesian coordinate system, which is also known as a number plane. You can see here that we are having, it is having a horizontal line. This horizontal line is known as x-axis and vertical line is y-axis. Okay, it is written opposite over here. This should be y-axis and this should be x-axis. Over here we are having, you can see, x-axis and y-axis. Okay, so along x-axis, this horizontal line is x-axis and this vertical line is y-axis. Vertical line is representing y-axis, horizontal line is representing x-axis. Okay, so how we are going to represent this? Horizontal line x-axis, vertical line y-axis. This type of plane is known as Cartesian coordinate system. Okay, this could be 2-dimensional or 3-dimensional. Normally it is 3-dimensional system, but for simplicity we represent just 2 dimensions because we can draw 2 dimensions on the paper. You can see 2 dimensions on the screen. You can see xy plane over here. It is not possible for us to draw z-axis over here correctly. Okay, because z-axis is perpendicularly out of this plane, so we cannot draw z-axis properly on the plane. So that's why right now we are just showing x-axis, the horizontal line, and y-axis, the vertical line. Okay, so this is our first quadrant, which is having positive x-axis and positive y-axis. You can see over here the quantities along x-axis are positive and the quantities along y-axis are also positive. So x and y, both quantities are positive. This is our first quadrant. In second quadrant, x-axis is negative and y-axis is positive. You can see over here x negative, y positive. Okay, so we are going to represent this ordered pair as x and y, negative, positive. This is third quadrant in which x-axis is negative as well as y-axis is negative. Both axes are negative. And fourth quadrant, x-axis is positive and y-axis is negative. So if we are just provided with the values, we can tell that in which quadrant these values are lying. Positive, positive, negative, positive, negative, negative, and positive, negative. So these are 4 quadrants in Cartesian coordinate system in 2-dimensional plane. Okay, so if we are talking about Cartesian coordinate system and we are plotting some points over here, you can see over here, if we are going to plot 2 and 3 over here, 2 along x-axis and 3 along y-axis, 3 units along y-axis. So we are moving 2 units along x-axis and we are moving 1, 2 and 3 units along y-axis. So this is the required point, 2 units along x-axis and 3 units along y-axis. 2 and 3, we can plot this point over here on Cartesian coordinate system. Similarly, we can plot -3, -1 over here, -3, 3 units along negative x-axis and 1 unit along positive axis, -3 and 1. Okay, and if we are having -1.5, -2.5, so over here we can plot it as -1.5 units along negative x-axis and -2.5 units along negative y-axis. So we can plot any point on the Cartesian coordinate system if we know those x and y coordinates. Okay, so with the help of Cartesian coordinate system, we can determine the position of the vector in plane or space. For plane, it specifies each point uniquely in a plane by a pair of numerical coordinates, which we have already discussed over here, which are the signed distances to the point from 2 fixed perpendicular directed lines. Which are those fixed perpendicular lines? X-axis and y-axis, measured in the same unit of length. Okay, these should be measured in same unit of length, x along x and y axis. Okay, plane are specified in terms of the x coordinate axis and y coordinate axis. We already know that x axis and y axis. Okay, and it can be written as ordered pair x and y. We can have a point having x and y points. Okay, and if we are talking about space, plane was two-dimensional just along x and y axis, but if we are talking about space, we should be having three axes, x, y and z axis. Okay, you can see here we are having x, y and z axis. Okay, you can draw just as you like it. You can draw x axis over here, y axis over here and z axis over here, or over here you can see that x axis is drawn here, y axis is drawn here and z axis is drawn here. It doesn't matter, all these axes should be mutually perpendicular. These should be mutually perpendicular to each other. You can see over here that we are having three intersecting planes. For space we are having three-dimensional. Okay, three dimensions should be there, x, y and z. For representing positions in space, the three perpendicular spatial axes generally designated x, y and z. Three axes are there. Okay, any point P may be represented by three signed numbers, usually written x, y and z. So we need three coordinates for complete specification of a point in space. Okay, if we are talking about space, three-dimensional coordinate system, so we are having a plane as well as that should be having some height. If you are standing at the corner of the room, then you can see that at the corner, you can consider that corner at the origin. Okay, this common point is considered as origin. Okay, the point where all these axes are meeting, this is known as origin. So the corner of the room can be considered as origin. The height of the room can be along z axis, and all those bottom, you can say bottom lines which are present on the floor, they can be x and y axis. With the help of that, you can understand three-dimensional system. Okay, so you can see here x, y and z plane, all three planes are mutually perpendicular to each other. Okay, as the screen or the paper, that is a two-dimensional surface, so it is not possible to properly explain all three planes. Okay, so you can see here that this is xy plane. Okay, so we are having xy plane with z is equal to 0. We are having xz plane with y is equal to 0, and we are having yz plane with x is equal to 0. So these three planes are mutually perpendicular to each other. Okay, x is equal to 0, yz plane, xz plane, you can see here this is x axis and this is z axis, that's why it is xz plane. This is x axis and this is y axis, so it is xy plane. This is z axis and this is y axis, so this is yz plane. Okay, so these three planes are mutually perpendicular to each other, and the central point is the origin. So for complete specification of any point, we need to specify three coordinates. Okay, so you can see over here that if we are talking about a point which is present over here, this point is changing. You can say with the change in location of this point, you can see x, y and z axes are changing. Okay, so this is basically three-dimensional space, x, y and z plane. Okay, so for complete specification of a plane, we need three, for a space we need three planes. Okay, so if we are going to draw the angles, if any vector A is having with x, y and z axis, with x axis it is making an angle alpha, with y axis it is making an angle beta, and with z axis it is making an angle gamma. Okay, so direction vector in space is specified by three angles, symbolically written as alpha for x axis, beta for y axis and gamma for z axis. You can see here, so all these angles are provided. Any vector in space, It makes an angle alpha with x-axis, beta with y-axis, and gamma with z-axis. So what about direction? If we are having this vector which is present over here, what is the specific direction over here? We cannot tell that it is directed this way. We have to specify its direction, proper direction. So if in this example displacement is there, and displacement is a vector quantity, so we need to report its direction. Okay, let's say if this is north, south, east and west direction, so in which direction this vector is indicated, in which direction it is pointed. So this direction, basically this is north of east and this is east of north. You can see there is a difference, north of east and east of north. This direction is south of west, this is west of south, north of west, west of north, south of east and east of south. Now from these directions you can see that what is the direction of this given vector. It is basically north of east. This vector, we have to take the angle with positive x-axis, so this will be north of east, so it is directed north of east. When we will study that in detail further, that will be more clear to you people. So this vector is directing north of east with positive x-axis. See, there is a difference between northwest and west of north. So this one is northwest and this one is west of north. Okay, so there is a difference between these two directions. So when you will practice that, you will come to know that which direction is which. West of north means that you have to start from north and move towards the west, west of north, and northwest means that you have to start from west and move towards north. That is the difference for the directions. Okay, now if we discuss some important vectors, if we are having equal vectors, what does it mean? Vectors having same magnitude and same direction. Let's say we are having two vectors, vector A and vector B, and these two are equal. You have to place arrowhead over here. Okay, so vector A and vector B, these are equal in magnitude. This symbol should be with arrowhead. Vector A and vector B equal in magnitude and they are having same direction. It doesn't matter what is their starting point, what is their ending point, their head and tail, where they are placed, just their magnitude should be same and their direction should be same, then they are known as equal vector. Negative vectors, vectors having opposite directions. If one vector is directed in this direction, okay, upward, and the other is directed in opposite direction, then what is this? Vector A and vector B are negative to each other. Their magnitude is equal, their direction is opposite. So we can say that these are negative vectors to each other, vector A and vector B. Collinear vector, vectors in the same straight line or parallel. So if these vectors are parallel to each other, they are directed along the same direction, they will be known as collinear vectors. Their direction is same. Coplanar, they must be lying in the same plane. Like if these vectors are lying in xy plane or yz plane or whatever, then we will say that these are collinear vector lying in the same plane. These are coplanar vectors. Okay, if they are along the same direction, they are collinear. If they are in the same plane, they are coplanar vectors. Okay, so null vector, a vector which magnitude is 0. What does it mean? Two equal and opposite forces acting on a point. Force is a vector quantity and we are adding two forces which are equal and opposite. Okay, so what we say that its resultant is 0. We will not say it is 0, we will say that it is a null vector, a vector having 0 magnitude. Okay, so another example, if a rope is pulled by two equal forces by two men, then it remains fixed on that place because of equilibrium forces. This is null vector. Okay, so if we are pulling a rope and that rope is pulled by two equal forces, equal and opposite forces, then there is no resultant force. So that resultant force is basically a null vector. Okay, so null vector, a vector having zero magnitude. We cannot specify that on the page, but we know that if two vectors are acting opposite to each other and their magnitude is equal, they will cancel the effect of each other, and the left is a null vector. Position vector, position of any point with respect to origin of a reference frame is known as position vector. Okay, position of any vector with respect to origin is known as position vector. So if we are having any point P, okay, and that point P is present over here, we are going to specify its location, and with respect to origin we are drawing a vector, and that vector will be known as position vector, which is telling us about the position of any point with respect to origin. Displacement vector, it indicates starting and ending point, that is change in position. Change in position, we will, if let's say that this is this point P is our starting point, and the point delta R is this point P is starting point, Q is ending point. So at P we are drawing a position vector R1, at Q we are drawing a position vector R2, then we are subtracting these two position vectors and we will get this displacement vector delta R. Okay, so R2 minus R1 is delta R. This delta R is basically position vector, which indicates starting and ending point, that is change in position. That's why it is known as displacement vector. Okay, so we can say that position vector from origin to the point which is asked in the question, we can draw, if let's say this point and this point is given in the question, then we have to draw a vector starting from origin and ending at this point. This is the position vector, this is another position vector, and this is basically the displacement vector. Delta R is displacement vector. It points from the original position. You have to, let's say if this is original position, then you have to make the tail of the vector over here, and if this is initial position, then you have to place the tail over here. Right now we are taking this as Ri initial and Rf final, so we will start from here to here, that is delta R. Okay, displacement vector. Average velocity vector, we know that formula of average velocity is delta R over delta T. Okay, average velocity is delta R over delta T. So we can see here that displacement vector and average velocity vector should be directed along the same line. Okay, because the formula average velocity is equal to delta R over delta T. So direction of delta R and direction of V average should be same. So we here, if this is starting point P1, this is ending point P2, and this is the direction of displacement vector, then direction of average velocity must be same as that of displacement vector. Okay, instantaneous velocity vector, if we are, what is instantaneous velocity? Basically the velocity at any particular instant. Let's say we are considering this instant and we want to check out the velocity over here. So then instantaneous velocity vector will be along the tangent. If we are taking this particular point, then at this particular point velocity will be along the tangent. Okay, let's say that we are having this particular point, then velocity will be along this tangent. If you are having this particular point, then velocity will be along this tangent. So instantaneous velocity vector is tangent to the path. Okay, average acceleration vector is in the direction of change in velocity. So if we are talking about change in velocity, then we will draw, first we will draw initial velocity vector, then we will draw final velocity vector, and then we will draw the average velocity vector that will be the same as that of average acceleration. Okay, initial velocity vector, final velocity vector, change in velocity vector, that will be the direction of average acceleration vector. Okay, all these vectors, most of these vectors are not in your book, but you should know about these vectors. Okay, that where these vectors are directed, how we are going to indicate these vectors. These are basic vectors which you people should know. Velocity vector, velocity vector is always in the direction of motion, An acceleration vector can point anywhere. Okay, velocity vector is always along the direction. You can see if motion is along this direction, and all these green vectors, these velocity vectors are directed along the motion. Okay, tangent to the points but along the motion. But you can see over here acceleration is directed over here, here, here. Acceleration is directed differently. What is the reason? Because even if velocity is changing, okay, even if body is moving, sometimes its acceleration is decreasing, sometimes its acceleration is increasing. How if we are moving in a car and if we are applying brake, at that particular instant acceleration is decreasing. Okay, but if we are going to increase the speed, then acceleration is increasing. Okay, so even velocity vector is directed along the direction of motion. Acceleration vector can point anywhere. It could be acceleration or it could be deceleration. Acceleration could be increasing or decreasing according to increase in speed or decrease in speed. Okay. What about unit vectors? Unit vectors are dimensionless vectors of unit length and used to represent the direction. Okay. So if we are talking about the unit vectors, what are unit vectors? These are dimensionless vectors, means they are having no unit. Okay, let's say that we are going to specify the direction of x-axis and y-axis, then we will plot their unit vectors over here. So what is the unit vector of this x-axis? This is a vector with a hat, a cap on it. Okay, small letter, small x with a hat. So this x hat is basically the unit vector along x-axis, and its magnitude is 1. Just 1 without any unit, because it is dimensionless. Okay, so it is just telling us about the direction, that if we are having any specified vector and with that vector we are writing x hat, it means that that vector is directed towards the x-axis. Okay, and if we are writing y hat with the magnitude of any given vector, then it means that that specific vector is directed along the y-axis. So this unit vector is only telling us about the direction, nothing else. It is having magnitude 1, so multiplying with any vector does not affect that vector. Magnitude of that vector remains same, just direction is indicated by this unit vector. Okay, so unit vector, it is generally represented by letter with a cap or hat over here. Okay, so we can represent a vector with a hat over here, just like we have indicated x hat and y hat. Okay, so a hat or cap is placed. For example, the unit vector for vector A is a hat. We can indicate the direction of vector A with hat, a hat. Okay, and unit vector is obtained. How it is obtained? By dividing a vector by its own magnitude. We have already discussed this thing, that let's say if we are having a vector A, it is completely specified by its magnitude as well as its direction. A hat is its direction. Okay, so direction or unit vector of a specified vector is equal to vector divided by its magnitude, because magnitude of these vectors will be cancelled and only direction will be left, which is equal to a hat. Okay, so a hat is the unit vector which is obtained by dividing vector by its magnitude. Okay, and unit vectors, we have discussed this thing, that we can check out that whether a vector is pointed along x-axis, y-axis or z-axis. We have given the proper names to those unit vectors which are along x-axis, y-axis or z-axis. Let's say that a vector which is perfectly along x-axis, that is represented by I hat. The vector, unit vector which is perfectly along y-axis is j hat, and the unit vector which is perfectly along z-axis is represented as k hat. Okay, so I hat, j hat and k hat are the unit vectors which are along x, y and z axis. So if we are specifying that we are having a vector A which is equal to 3I hat, so we will come to know that it is 3 units along x-axis. Okay, and if we are having a vector which is equal to -5j hat, it means that it is along negative y-axis, 5 units along negative y-axis. Okay, so with this unit vector we come to know that what is the direction of the given vector. So you can see over here that if we are having along x-axis we are having this coordinate 1 0 0, it means that I vector is having these coordinates 1 0 0, 1 unit along x-axis and 0 0 unit along y and z axis. Okay, j hat is having coordinates 0 1 0, x is 0, y is 1 and z is 0, and k hat is 0 0 1, x and y are 0 and k z axis is having 1 unit. Okay, so unit vector, it is having magnitude 1 and it is specified with the, it is in the direction of the given vector. Okay, and normal vector, it is again a unit vector, normal or perpendicular to plane or surface at any point. It is represented as n hat. Okay, so if we are having any given surface and we want to check out the direction perpendicular to that surface, okay, so that particular vector is known as normal vector. Okay, and let's say that we are checking out this direction normal to the given plane, this is represented by n1 hat, and if we are checking out this perpendicular direction, that will be n2 hat. So if we are drawing a line which is 90 degrees to the given plane, that is given as perpendicular or normal vector, which is known as, which is represented by n hat. If it is having magnitude of 1, it is just specifying the direction, then it is a unit vector which is specified by n hat. Okay, so unit vector is specified by n hat. It is not telling us about the magnitude, it is just giving us the direction. Okay, so it could, this direction could be along any plane. XZ plane is having a direction, normal vector, it is indicated over here. So it could be normal to the vector, could be along any plane. Okay, so now if we are standing over here and we know that magnitude is 0.5 miles and we exactly know the direction, that the library is located just along this direction, so we can move towards this direction. So if we are having magnitude as well as direction, then we can move towards the library. Okay, so that was all for today's lecture. I would like to end my lecture with this quote, that imagination is more important than knowledge. Okay, you just not need to memorize all these things, but you can imagine that where these vectors are applied, what is going on over here in the universe, you have to imagine about that. The more you imagine, the more you come to know. Okay, so imagination is more important than knowledge. Thank you so much.